All right, we'll go ahead and get started. So for this discussion, we'll be doing some proofs and then some sets. Just as a quick reminder, remember that on Tuesday, you'll have your quiz 2, so that'll be over proofs. So make sure that you study for that, look at past discussions, past recitations, as well as the practice quiz and solutions that have been posted. And if you have any questions on anything, please stop by. There'll be office hours tomorrow and a lot of office hours on Monday as well. So please stop by if you have any questions before that second quiz. So first we're going to do another induction problem just to kind of help prepare for quiz 2. So here we're asked to do this proof by induction and prove that n factorial is greater than 2 to the n for all n greater than or equal to 4. And then there's just a reminder on how we define what n factorial is, and it's just n times the preceding values of n until we get to 1. And so this will be a similar form that your questions on the quiz will come. They'll tell you which proof technique you need to use when you do the proof. So we've got this induction problem. We always start our induction problems the same way. So first we need a problem statement. So can somebody give, what would our problem statement be for this problem? So close, we had somebody say, so it would be n factorial greater than 2 to the n, perfect. So our statement P of n would be that n factorial is greater than 2 to the n. And then we need the caveat for n greater than or equal to 4 in this case. So we've got the problem statement. Then we need to do the base case. So what would the base case be for this problem? Yeah, perfect. So someone in chat, we have n is equal to 4. 4 because that's the smallest possible value we could have for n. And then we just need to show that the base case is true. So 4 factorial, well, that's just 4 times 3 times 2 times 1. So that's 24. But 2 to the 4 is equal to 16. And 24 is in fact greater than 16. So we have our base case is true. So now that we've done our base case, now we need to do the induction hypothesis. So in this case, what is our induction hypothesis? Yeah, so P of n is true. We could do that P of n plus 1 is true and show that P of n plus 2 is true, but we usually don't do that. We usually stick to either assuming that P of n is true or assuming P of n minus 1 is true. So yeah, let's go ahead and assume that P of n is true. So we're going to assume P of n. In other words, we can assume that n factorial is greater than 2 to the n. And then the final step we have in induction is we always have the inductive step. And that's where we show that P of n implies P of n plus 1. So go ahead and take a minute or two just to get started on this inductive step portion of the proof. So for the inductive step, we would start, in this case, we would start with n plus 1 factorial, because we want to prove this statement is true for n plus 1. We want to prove that n plus 1 factorial is greater than 2 to the n plus 1. So does somebody want to explain, just by raising their hand, just muting themselves, how we can start this inductive step portion of the proof? Yeah, sure, Dylan, go ahead.
So n plus 1 factorial is equivalent to what was it? It was n factorial times n plus 1, I think.
Yes, perfect. That's how factorial, because factorial is just the multiplication of all the elements lower than that value. So n plus 1 factorial would be n factorial times n plus 1. Perfect. And then what can we do next? So what can we do for the next step of this proof? We've got n factorial times n plus 1. Probably know something about n factorial. Yeah, go ahead, Dylan.
You could substitute n factorial with 2 to the n, because in the hypothesis we deduced that they're equivalent.
Yeah, in the not that they're equivalent, but the one's greater than the other.
Oh,
so
yeah.
remember, our inductive hypothesis said that n factorial was greater than 2 to the n. So we can replace n factorial with something smaller. In other words, we can replace it with 2 to the n here. And then we need to introduce a greater than symbol here. Any ideas for the next step? Remembering we want to end up with this is greater than 2 to the n plus 1. So this is a little tricky portion. This little step here to get from having 2 to the n times n plus 1 and getting 2 to the n plus 1. Now, what I like to kind of think about this, when we ever have less than or greater than symbols, we can often do a lot of tricks to make it work out. And the reason why is just because we can pick smaller values on this side. So if we just want to have a greater than symbol, we can replace this right-hand sign with any value smaller than any of these values. So if we want to end up here, so this is where we want to end up. So in other words, we wish that n plus 1 was equal to 2 here. Because if we had n plus 1 equal to 2 here, then we would immediately have this next step, 2 to the n plus 1. But since we're using greater than symbols, what we can do is we just need to show n plus 1 is greater than 2. And then we can make this substitution that this is greater than 2 to the n times 2. So how do we know that n plus 1 is greater than 2 in order to make this substitution? Yeah, because the base case is 4. So since n is always greater than or equal to 4, n plus 1 will always be greater than or equal to 5. So n plus 1 is always greater than 2. So we can make this substitution where we take this statement and we replace it with something smaller than it. So this greater than symbol holds. And then we would just end up that this is equal to 2 to the n plus 1. Now this is a little bit tricky. So what often helps is if I write it out in a line, and I think that helps students kind of understand how these greater than symbols work. So if we write it out just in a straight line, then everything on this side of equality is greater than 2 to the n times n plus 1. And this is greater than 2 to the n times 2, which is equal to 2 to the n plus 1. And then we have our original statement greater than 2 to the n plus 1. So are there any questions over this part? It's a little tricky to kind of figure out this step here, but any questions on this induction statement? And then we just write a little conclusion here while everyone's typing questions. So it doesn't look like there's any questions then. Cool, so go ahead and move on to the next problem. So here we've got a pigeonhole problem. And so we're asked to use the pigeonhole principle to find the fewest number of times that you must roll a standard 6-sided dice before you can be assured that at least 10 of your rolls have resulted in the same number. So we've got a pigeonhole problem. Remember, we want to figure out what values m and n are, is always how we start the pigeonhole problem. So we want to, we have these equations where we have m plus 1 is equal to something, n is equal to something, and m times n plus 1 is equal to something. And we want to figure out what these values mean whenever we do a pigeonhole problem. Yeah, perfect. So we've got, it's not quite equal to 10, but that was a really good guess. It's not m times n plus, so there was somebody in the chat who said that m times n plus 1 is equal to 10. It's a good guess, and there is an equation on here that is equal to 10. But remember that m plus 1, or can anybody tell me what does m plus 1 represent? The value of m plus 1. Yeah, so somebody put it, so the value here is 10, and this 10 represents the number of objects at least in one box. Yeah, somebody else said, yeah, we want 10 rolls to be in the container. Yeah, so m plus 1 is equal to 10. And then can somebody give me the value for n in this case? Yeah, 6. So we got a lot of comments saying 6. And remember that n always represents the number of boxes. How did we know that we needed 6 boxes? Well, because we're rolling a standard 6-sided dice, and we want to count basically the number of rolls that results in the same number, then what we're really doing is we kind of have these 6 boxes set up. If we roll 1, 2, 3, 4, 5, 6, and that's how we get n is equal to 6. So with these two values then, m plus 1 equals 10, that gives us m is equal to 9. So m times n plus 1 is 9 times 6 plus 1, which is equal to 55. And what does this value represent, 55? Or what always does m times n plus 1 represent? Yeah, so this is the total number of times. We need to roll the dice. Or the total number of objects that we can put into these boxes, such that we're guaranteed at least one of the boxes has 10 elements in it. So we could kind of explain by the pigeonhole principle, if we place 55 objects into 6 boxes, at least one box will have at least 10 objects in it. So after 55 rolls, at least 10 rolls will result in the same number. Another way you can kind of think about this is that, like, in the worst case, we could have placed 9 objects in each of these boxes without any one of them having 10. So we would have placed 54 items here if we placed 9 in each box. And then when we go to place the 55th item, we have to place it in any one of these boxes, and one of them will inevitably have 10 elements in it. So this problem just goes to, is kind of designed to show that oftentimes when we're doing pigeonhole problems, we're usually given what m plus 1 is and what m times m plus 1 is, but not always. So you need to always look at the statement to make sure that you know which one of these 3 values were given in the problem and which one we need to go find. So any questions on this problem? Awesome. So we're going to move away a little bit from proofs, which is just going to be what your quiz 2 is on. And we're going to go to sets, which is what the homework and what we've been learning in lecture. So here we've got this example problem where we're interested in the elements of sets. So we've got this set A that contains all elements that are 4 times a natural number. B is the set of all y where 2y is a perfect square. And C is the set of all z where z squared is less than 1,000. And so we want to find 5 elements in the following sets. Well, first, what we should probably do is think about what are the elements contained in A, B, and C. So first, let's try to think about what are the elements in A, what are the elements in B, and what are the elements in C. So you just want to go ahead and take about a minute to think about what are the elements if we just wrote them out as numbers for each of these sets. Okay, so does somebody want to give, what are the first few elements in the set A that we have? So they're the form 4k, where k is a natural number, right? So what are the first several elements we could have? Yeah, so somebody said, yeah, 0, 4, 8, 12, 16, perfect. We start with 0 because remember the way we define the naturals is 0, 1, 2, 3. Just remember, be careful if you're looking at stuff on in other textbooks or other resources. Other textbooks sometimes define the naturals without 0. But in this class, we're taking the definition that includes 0. etc. And then what about for B, where 2 times y is a perfect square? So remember here, what are our perfect squares, right? Well, the perfect squares, these are the numbers 1, 4, 9, 16, 25, 36, etc., etc. And so we're looking for values such that 2 times a number is equal to this. And remember, we're looking only at the positive integers here, so we're not considering 0 to be a perfect square here because y wouldn't be a positive integer then. So those values, so we could have 2 would be in the set B because 2 times 2 is equal to 4, which is a perfect square. Yeah, somebody put, so yeah, we could have 2, 8, 18, 32, 50. Yeah, perfect. And for each one of these, we could check that if we double each of these values, we would end up with a perfect square. And then lastly, we've got C, where C is an integer, and Z squared is less than 1,000. So here we just need to find whatever value squared gives us close to 1,000. So in this case, we would start with negative 31, negative 30, etc., all the way up until we get to 30 and 31. Once we get to 32, that's equal to 1,024, and so we'd be over that 1,000 threshold. So now we're asked to list 5 elements in this set. So what are 5 elements in the set? Anyone have any possible values? So we're looking for elements that are, since we've got A intersect B union C, looking for possible values that are in A and either in B or C. So let's look for one that we could pick is, we could pick 0. 0 is in A and 0 will be contained in C. 4 would be contained because it's in A and C. 8 would be in A and would be in C. 12 would be in A and would also be in C. 16 would be in A, also in C. So you might think that, hey, we don't really need B, but that's not quite the case because later down the line, we'll have elements such as 32 that are in A and in B, but not in C. So lots of examples, but this could give us 5 elements that are in A intersect B union C. Any questions on that? And yeah, perfect. Somebody put that in chat as well. Yeah. And yeah, not anything just between 0 and 31, because we just need to check that it's also in A. So any value in A between 0 and 31 would definitely work. Awesome. So let's go ahead to the next problem. So here we've got a problem with Venn diagrams and sets. So we need to use Venn diagrams to verify the following properties. And so here we're going to verify that absorption properties are true. In other words, that A intersect A union B is just equal to A. So what we need to do is we need to look at what's happening on the left, the Venn diagram of the left-hand side and then the right-hand side. So we're going to look at when we have the set A and the set B, how are they interacting in these two examples? So if you just want to go ahead and take about a minute to go through these example Venn diagrams. All right, so let's go ahead and get started. So first I want to see if anybody, there's something missing in these Venn diagrams that we always need to add. Does anybody know what we would add in the first one around these? Yeah, yes, perfect. So we need to add, yeah, the universal set for all of these, because we've always got this universal set that sets A and B are inside of. So first we'll look at, and so we'd have that for each one of these. So first, let's take a look at, here we'll look at A, then we'll look at A union B, and then we'll look at A intersected with A union B. So when we look at A, we'd have this shaded region. We represent the set A. When we're looking at A union B, we're shading in all of these values here. And then A intersected with A union B would just be, is all the values that are in both A and an A union B, all the areas shaded in. And so that's this region. Is shared by both A and A union B. And then on the right-hand side of our problem statement, we just have A. And if we look, these two are equivalent. So we can verify that the absorption property is correct by these Venn diagrams. Any questions on that? Awesome. Yeah, just the one thing to remember with these is when you're trying to Venn diagrams, don't forget the universal set that encapsulates all of your Venn diagrams. So now we have another Venn diagram problem. So here we're going to use Venn diagrams to see if this more complex statement holds, so that A subtract B union B subtract C is a subset of A subtract C. So if you just want to go ahead and take about a minute to go through the Venn diagrams for this statement. All right, so let's go through this statement. So first, here we're going to take a look at what does it look like, what does A subtract B look like? Then we'll look at B subtract C, and then we'll look at this entire statement. So for this first box, so we've got A, and we're going to subtract out all the elements in B. So we're going to shade in the region of A, but not any of the region that's shared by B. So we'd have this region. Then for B minus C, we'll shade in the region of B, but not any region that's also in C. So we'll have this region shaded in. And then the union of these two, we'll just shade in both of these areas. So we have something that looks like this. And then for this bottom statement, we're going to take a look at the right-hand side. So A minus C. So here we're going to shade in all the region of A that's not in the region of C. And so we'll get something looks like this. And then if you just want to type in chat, do you think that this statement holds then? That A minus B union B minus C is a subset of A minus C. Any guesses whether or not this property is true or false? Okay, so we've got a lot of guesses for true. Okay, we've got some more on false. Okay, so it looks like we're a little bit split on this. So let's kind of go through it. So when we're looking for a subset, what we want to be guaranteed is that everything in this has to be contained in this set. And when we look over here, for this to be a subset, we would need elements in B. For this diagram over here to be a subset, we need elements in B to be contained over here. We would need, because we could have had elements in A minus B and B minus C that ended up in B, because we have this area of B shaded in, but this area is not. So this is not a subset. And let's, if you're still not convinced, let's do that with a counterexample, and we'll take a look at that. So one counterexample, just a simple counterexample, and I'd always look for simple counterexamples, so just sets with very few elements in it will often be sufficient enough. So let's look at the set when A just contains the value 1, B just contains the value 2, and C contains the value 3. Then if we did A subtract B, that would just be the set 1. B subtract C would just be the set 2. And A minus B union B minus C would be the union of these two, so that would be the set 1, 2. But A minus C, set A is just 1, subtract out elements that are 3, there's none. So this is just the set 1. And 1, 2 is not a subset of 1. So this does not hold in general. So any questions on this problem for why this statement does not hold in general? Yeah, good question. So somebody asked in chat, had the left-hand side and the right-hand side been switched, would it have been true? Yes. Then that would have been true. So it is true that A minus C is in fact a subset of A minus B union B minus C. And we can see that over here. For it to be a subset, we need all of the shaded regions contained in this A minus C diagram to be contained in this diagram over here. And that is in fact the case. Yeah, really good question. So let's go ahead and move on to the next problem. Whoops. So here we've got a problem dealing with power sets. So we've got, we defined what our universal set is, and then we have sets. We're not going to use set A in this problem, so I'll just scratch that out. Sets B and C, and we want to find the power set of B intersects C. So does somebody want to type, what is the intersection of these two sets, B intersects C? Yeah, perfect. So somebody typed in chat, it's the set 1 containing 1, 2. Because 1, 2 is in both sets B and in set C. And then now we want to look at the power set of 1, the set 1 condom 2. So what sets are going to be in the power set of this set? Remember, the power set is the set of all subsets. So there's one set that's always in every power set. Yeah, so we've got, yeah, perfect. We've got answers. So someone says the empty set. Yeah, so we've got set with nothing in it. That's always in the power set. The empty set is always a subset of any set. And then we've got the set containing 1, the set containing 2, and then the set containing 1, 2. And remember, the power set is a set of sets. So this is not equal to if we just wrote 1, 2, 1, 2. Remember that the curly braces have a specific meaning in regards to sets. So we're just looking at this here. Any questions on this problem? One easy way to check that we did this right is that the number of elements in B intersects C is 2, and the number of elements in the power set of some set I was going to use the standard n there, but I don't want to confuse any of you by having the same n. Is always going to be 2 to the n. So 2 to the number of elements in the set is going to be the number of elements in the power set. So in this case, we have 2 to the 2, which is 4. And we've got 4 elements in the power set. So that's a little quick step check to see if we have at least the right number of elements in the power set. So let's go ahead and move on to this next problem. So here we're going to identify which of the following statements are true. And for each statement that's not true, we're going to provide a counterexample. So go ahead and take just about a minute to think about some of these problems, and then we'll go through whether or not they're true. So does anybody have any guesses for the first, for part A, if you think it's either true or a false statement? Yeah, perfect. Somebody says true, and that in fact is what it is. We don't need to prove it. We're not asked to prove it in this statement. But some of the intuition behind this is we already knew that A was a subset of B. If we take the Cartesian product with the same set, then this is always going to be contained in this statement over here. Because for every value A, that Cartesian product with A cross C is going to be contained since all of those elements were in B. So this statement's going to hold. It's just a little bit of intuition. And then what about B? Is that a true or false statement? So this one is in fact false. And we can show a little counterexample. So whenever you're providing counterexamples, I find that often the smallest sets are the easiest to work with. And in fact, sets with one element often provide those counterexamples for these simple problems. So what we can do here is we can just say, well, what are we looking for to find a counterexample? Well, here we're looking for, since we're doing the cross product, the first element of the cross product here is going to be either elements that are in A or B. But the first element in the cross product here, since we're taking A squared, recall that A squared is just A cross A. The first elements in these cross products are going to come from A. So as long as we find a set that has some element in B, we're going to be able to disprove this statement just by looking at the first elements of the cross products. So if we look at the set where A is the set 1 and B is the set containing 2, then A union B cross A minus B is going to be, well, A union B, that's just going to be the set 1, 2, cross product with the set A minus B, well, that's just going to be the set 1. And then applying the cross product, this will be the set 1, 1. Remember that these are tuples, so they need parentheses on them. This is not the same as this. So make sure you're careful when you use curly braces and when you're using parentheses, because those mean something very different when talking about sets. Okay, so that would not be true. And then we can take a look at, well, what's A cross A minus B cross B? Well, A cross A, that's just the set containing 1, 1, the tuple 1, 1, and we're going to subtract out the set containing the tuple 2, 2, and that's just the set containing the tuple 1, 1. And notice these two are not equal. The set containing 1, 1. In the other case, we have the set containing 1, 1 and 2, 1. So those are unequal. And then any idea for C? If that statement would be true or false? Okay, so we've got someone that says true, got a couple other people that say true. In fact, this is not true. And so let's go through a quick example of why these are two different values. So if we take, again, a simple example, so we've got A, the set containing 1, B, the set containing 2, and C, the set containing 3. Well, if we look at A cross parentheses B cross C, then we're going to do, since we have parentheses, we're going to do B cross C first. And the set B cross C will be the set containing the tuple 2, 3. And then when we cross that with A, that'll be the set containing the tuple 1, the tuple 2, 3. But when we do A cross B cross C, then we're going to do the tuple A cross B first. And that'll be the set containing the tuple 1, 2 cross C, which will be the set containing the tuple 1, 2, the element 3. And these are not the same. One is a tuple containing a value and another tuple. Well, the value 1 and then the tuple 2, 3. The other one's a tuple containing the tuple 1, 2 as the first value and then the value 3. And so these aren't the same. Any questions on this problem? Any of these set properties? Cool, so we'll just go right ahead then. So we just have about a minute left, so I'll just quickly explain this one. So in this one, we're looking at why these sets have the same size. So it's similar to the last problem we did, where we noticed that parentheses have a different meaning when we're doing cross products. So for example, this cross product here, this is going to be elements that are contained, elements little s1, little s2, tuples like this, so little sk. Here we'll have elements like little s1, little s2, little sk minus 1, and elements in sk will be our tuples. So while the elements are different, the takeaway here is that the order of operations of the Cartesian product does not change the size of sets. No matter what order we take the cross product, the Cartesian product in, we'll always end up with elements that are the same size. And just the reason is because we'll still be considering all the possible cross products. But in this case, these elements will just be in a tuple, the elements s1 through sk minus 1. And in this case, they'll be contained just in this tuple over here, is a little brief explanation. And then there's a final problem that you can go ahead and work through on your own. And it's just proving that if A union B is B, then A union B intersect with A naught is equal to B. And so you can go ahead and work through that and go to any office hours if you have trouble with this. Don't forget, just as a last reminder, that quiz 2 will be next Tuesday. So make sure you study, prepare for that. Go to office hours either tomorrow or on Monday. If you have any questions on proofs, that'll be on quiz 2. Remember that sets will not be on quiz 2. That'll be on the next quiz. And then if you have any other questions, it'll be run for a couple minutes. But thanks, yeah, you're all good to go ahead and go.